Hi, my name is Chunhui Zhu. Welcome back to my tutorial, Time Series Analysis using Python. This is the main book. It's for my guidance for my tutorial, Time Series Analysis, Univariate and Multivariate Method by Dr. William W.S. Wei. I will do a little bit of review from the last video. I will going to share what I have discovered for Python code. In part 2, we're going to learn the time series important tools, ACF and PACF. You may have seen this graph in many of the data science research papers. Today, we get deeper understanding these little legs. Let's start. When we talk about stationary in time series, we talked about covariant stationary. Stochastic process is said to be normal or Gaussian process if its joy probability distribution is normal. Since it followed the Gaussian process, the first two statistic moments are equivalent. Now, I want to share my discovery for a Python code random.ranin. Last time, I used this function to generate the 6 integers from 1 to 6, which are follow the uniform distributions. But I tried to run my program many times. My sample mean never get close to the expectation value, 7. Then I tried to discover what my computer given to me. Then I found I never get any 6 in my samples. Then I increase the size of the random sample. I'm still not getting 6. I run it 20 times, still not getting 6. So in the future, if you are going to use random functions, I more likely suggest you increase 1 in your maximum boundary. I shared it with you because I found this definition for this function is not correctly defined in many of the websites. Friends, spending time to run your algorithm will improve your accuracy of your outcomes in the future. Let's come to part 2 to learn ACF and PACF. Autocorrelation function in time series analysis represent the correlation between the zt and zt plus k from the same process, separate only by k lags. Autocovariance gamma k is equal to the covariance between the zt and zt plus k. Autocorrelation functions rho k equal to gamma k divide gamma 0, and gamma 0 is equal to variance of zt. Let's look at the property of the ACF. The first property, gamma 0 equal to variance of zt, rho 0 equal to 1. I hope you can remember rho equal to 1 from this graph. The first is rho 0. It's always equal to 1. The second property, absolute value of gamma k and rho k, they are less than and equal to gamma 0 and rho 0. The third property, gamma k equal to gamma negative k, rho k equal to rho negative k for all k, so that they are the even function and symmetry about the lag k equal to 0. Friends, not all the ACF satisfy the first 3 properties. The fourth one are the special one. This ACF, you can see all the lag is above 0. This ACF normally to use to evaluate the polynomial models. Suppose your model have a lot of independent variables. You can use this method to check which independent variables are not significant from the dependent variables, so that you can reduce the size of your models. And here, gamma is the mean squared linear regression coefficient, which is minimize the expected value of the difference zt plus k and hat t plus k squared. This is very important, since if these terms reduce, it also reduces gamma and rho. Let's learn some complex formula for ACF. Consider about a stationary process zt. We assume that E of zt equal to 0, then hat zt plus k is the best linear estimate of the zt plus k. These three complex formula I copied from the book. Friends, don't worry about that. We learn them step by step. Take a look at these small pictures. Consider about in the unit of time, zt as the component of the AT and BT combined. Suppose AT functions and BT functions are stationary functions in all the time, so that the sequence of zt is a stationary process. Let's take a look at this horizontal line. zt1 is a linear function between t0 to t1, and z2 is a linear function from t1 to t2, and keep it so on to the end. Let's look at the bottom of these functions. From the left, I set t equal to 0, k with a different value, increasing from 1 to 4. I derive this hat zt depends on the formula from above. Hat zt is depend on the previous steps is backward one by one. So for hat z1, your term is here is nothing in the previous, is nothing to compare. So hat z1 does not exist. For hat z2, you have z1 at the previous, so that as this as dependent values. Hat z2 is at this term. It has a z1 value to compare. And hat z3 is at this term. You have z1 and z2 to compare. And then hat z4, you have z1, z2, z3, three terms to depend. Now, take a look at the gamma functions. Gamma 0 equal to variable z1, and gamma 1 in terms in the second, it has the covariance between z1 and z2. Then the gamma 2, you have another two legs in previous, so that you can compare and calculate the covariance among them. So we can do the extensions to gamma 3 and so on. Once you have all this gamma value, you can derive your rho value. And remember, rho 0 is always equal to 1, and rho k equal to gamma k divide gamma 0. Now, you get all this rho k by knowing all this gamma k. Now, you understand how the computer compute ACF for you. Take a look at all of these functions. They all are linear functions. To calculate such linear functions, we can use a camera rule. Now, Let's look at the PACF, partial autocorrelation function. It's much easier than ACF, but you need to understand ACF before you understand the PACF. The PACF is like to investigate the ACF after remove their mutual linear dependency. You think of ACF as like to do the first derivative of a function. That is the first law. The second derivative is the partial autocorrelation functions. It's the speed of the slope. The following two are the partial autocovariance function and the partial autocorrelation functions. Let's see how they calculate it. Based on previous row-k linear systems, we use the Cramer rule to solve these linear systems. This is how the Cramer rule solutions for calculated the term of phi kk. Now, you understand what your computer done those calculations in PACF. Great job! Now, let's start the practice coding in Python in following steps. This is the previous example from the last video. For this covariant stationary sequence Y, we're going to plot the ACF and PACF. Let's load a statistic package, statisticmodels.graphs.ts+, and from this package we import plot_ACF. And also from the same package we import plot_PACF. We need to show the graph, so we need to import the pyplot from the matplotlib. The plot_ACF function is very simple. The first is the Y sequence. This is our data. The alpha set it to 0.05, which is mean the autocorrelation of the leg only has a 5 chance fall outside of the grouping. Now, I set the leg equal to 30. The leg is the k. K can be greater and equal to 1 and less and equal to n-1. We have the 100 number in Y, so the maximum for the k is 99. And here is the same meaning for PACF. Let's run this code. See how simple Python do this job for you. Friends, if this helps you to understand the stationary, the ACF and PACF, please give a thumb up. I will see you in the next video.